And all of these that I'm going to talk is about what I've been doing for the last, I don't know, 25 years on trying to create these intelligent robots. So there is a quest, I've been pursuing this quest for autonomous intelligent robots in the sense of trying to integrate the ability to autonomously sensing, making decisions, achieve goals, learning from experience, and eventually actuating. So our research has always been on trying to really bring this AI part, the task, the actual learning, the objectives, the planning, into the robot world and trying to close this loop, this wonderful loop of autonomy. So throughout the talk, I'm going to use 3 different platforms that I've been working on. My talk is many videos, so I'll first illustrate the 3 domains, and then I'll go into. As all of you probably know, I've been involved with robot soccer for an eternity. So this started in '97. In fact, I was here in '96 for an event before RoboCup. And the actual problem is very complex. So you want to have these little creatures, for example, in this league, the small size league, being able to respond to adversaries and planning and automated completely, no human in the loop. You have 20 minutes to play a game. You are supposed to win, very clear objectives. And then they pass again, and eventually they shoot. So the problem becomes to have this automated planner device, given the position of the wall, this is a repetition, to pass to this robot, the robot passes back, hits this one, and eventually makes another pass, and until the plan, the objective is accomplished, the planner doesn't start autonomously. We have also been working on Baxter to try to have Baxter perform tasks. This doesn't include vision itself. The robot knows where the different pieces are, the different objects, and it needs to plan some task of moving the robots to specific locations, and it does plan autonomously to perform these tasks. And then finally, I've been working on this problem of mobile service robots, which was going to be mainly the core of my talk. And these robots, called cobots, for collaborative robots, literally move in our environments completely autonomously, traversing the 9 floors of our building, the building next to ours, which is connected by a bridge, an indoor bridge. And we also have taken it to New York, to NYU, when I was on sabbatical. And there have been many contributions on these cobots, and it has been a wonderful experience having lived and continue to live with these robots. In fact, I moved my office to 1 floor above when I became head of machine learning, and now I have cobot right next to me in the next office. He has an office of its own, and when it needs to bring someone to my office, it's cobot who goes and brings the person to my office. So this is like reality. And this type of experience that I've had have led me to the talk that I'm going to give you today. And basically this talk includes 2 main areas. First, I'll tell you very briefly about autonomous robots, and you probably know about these mobile robots. And then I'll mention all this issue about peer interaction with humans. So let's first delve into, very briefly, into this specific problem of having robots be autonomous, the AI side of the robot. So even if the robot moves by itself and eventually has to move, when we actually want the robot to be executing or answering commands from the humans, we have to create methods for these users to talk with the robots. And so we developed a web-based interface, and with my students Brian Colton and Rodrigo Venturo, who was visiting us. And this specific web-based interface allows people to select tasks that include navigation from one place to another. And then these task requests are given to an online centralized scheduler. We also have versions in which it runs on the robots. But basically, then the robots get assigned to different tasks. Very briefly, these tasks have been scheduled also, so like I said, these multimodal requests we can schedule on the web, on the touch screen on the robot. We can type, we can speak, we can send SMSs. And this problem became the thesis of my student Brian Colton, who is now at NASA. And Brian did a very interesting thesis on how can we schedule these multiple robots to actually transfer items between them. And that was really a very beautiful algorithm in which the robots plan to meet in the specific place and eventually get these robots transferred from one to the other to optimize the final total travel time. So I'm not going to talk more about these, but in these tasks, one of the things that they actually do is, like I was saying, escort people to my office. So this is Eric Horvitz from Microsoft Research being escorted to my office. He's the only generous person who actually videotaped the experience, so I get to see what does it mean to be escorted to my office. And here is Eric following this robot, which was waiting for Eric at the elevator, and eventually goes through these corridors with glass corridors and walls and all sorts of different environments, and takes the right turn, and Eric arrives at my office, which is at the end of that corridor on the left, and I'm not going to go all the way to the end, but basically the robot is able to take anyone that visits me to my office. Okay, so come to CMU, and you'll get to be escorted by Cobot. So this particular ability is, this is a single slide on how they actually navigate and localize. And they are given a map. This is the thesis of my student Joydeep Biswas, which I'll mention in a second. And basically these robots use a vector-based representation of a map. It's not a learned map, but actually Joydeep is learning this map. But the interesting thing about this architectural layout of the map is that it shows what's static in the environment. The walls don't move, in principle, and the robots can use all of these walls to localize. So here is a robot. I stopped the video just to explain. This is the robot, slightly lost in the environment. It thinks that it's somewhere here. And here is the raw depth image. Cobot does not use RGB, only uses the depth of the connect. And basically also for privacy purposes, I believe. And here is just explaining how planes are detected in the image. The color means distance, just encodes distance, and these little kind of dots are normals on samples that identify planes. So you'll see that at a certain point, the robot is going to be able to see a little bit of that wall there, and then when it sees that wall, it's capable of reducing its uncertainty, given the map that it has, plus the wall, plus the corner. It's is enough for the robot to actually decrease its uncertainty and know where it is. So when you see the robot moving around in our corridors, that's basically what it's doing all the time. Finding walls, mapping to a vector-based representation of the map, and navigating a route plan that was planned by the scheduler and planner for the task. Now, the problem that became very important at CMU and everywhere is that the environments where these robots move are very dynamic. And therefore, there is always the problem of things that are not in these floor plans of the building, of course, tables and chairs and all sorts of other things that move. And how could we use them for actually improve the localization? So Joydeep Biswas, in his thesis, introduced this concept of episodic non-Markov localization, which enables the robot to use in a non-Markovian way the local features that are perceived as short-term versus the long-term features of the environment, that's the walls. And here is Cobot at NYU, at the CUSP Center from NYU, and moving after one day of arriving there, and we just downloaded the PDF file with the floor plans of the building, and it traversed more than, I don't know, I think it was about like 200 kilometers in this building during about 1 month, month and a half. And this robot used all those other features, tables, chairs, things that were not in the map, like all these file cabinets and specific other tables that kept changing in this environment as local features that were able to be used in a non-Markovian way. So I invite you to read these papers and delve into this issue of combining the long-term features of an environment with the short-term features of the environment and devising an algorithm that combines Markovian localization with non-Markovian localization, ignoring the people that move the dynamic features. So you end up breaking our sensing in what's long-term, what's short-term, and what's dynamic. You ignore the dynamic features for localization, you use the long-term features for Markov localization, and you use the short-term features in a non-Markovian way. So very effective. And it led this robot to move around for many kilometers, and it still moves everywhere. In fact, we have 4 of them. Joydeep has 1 with him at UMass, which I very generously let him take with him, and I kept 3 at CMU. So the interesting thing also is that these mobile robots ended up having this second kind of like function, which became the fact that because they so accurately know where they are in the building, and they can localize so accurately, by installing a sensor on these robots, they are able to actually collect the most accurate maps of any quantity. So they are actually mobile data collectors. And here is the robot collecting Wi-Fi data in the, I believe this is the 7th floor of Gates. And here is every single kind of like position in the building as detected by the robot with an accuracy of about 5 centimeters gets to be assigned to a particular value of the Wi-Fi data. So these autonomous robots, this is like 10 minutes of an overview of basically 2 or 3 PhD theses. But what I wanted to focus more today on the rest of the talk is really on this problem of this peer interaction with humans. So the robots actually move. The robots are capable of actually traversing the space. It took us a long time to get it to be robust and not just a demonstration, a prototypical demonstration. The robots are completely deployed in our environment. But there are humans in the building. So these robots are not up in Mars. They are not down volcanoes. They are not underwater. They are in humans' environments. And that became quite an interesting technical and research challenge to address. So the first use of these humans was what I termed symbiotic autonomy, in which these robots are capable of proactively and autonomously ask for help when they can't do something. So basically, these robots buy an elevator because they currently don't have arms, and I don't foresee that they will have arms to do a lot of things while moving for a long time, at least in my lab. These robots move everywhere, but they get to the elevator and they basically cannot press the elevator button, or they cannot pick up things to put in their baskets. Now, they don't have arms, but they have a basket. And like I've said many times, a basket is almost as good as arms, because you can put things in the basket and they carry things inside of the basket. So they basically ask for help. Can you please press the elevator button? Can you hold the door so I can go in? Can you put things in my basket? And they can also query and learn from the web. So here is an example. I need the sound now.
Copy to the lab.
In which the robot is asked.
This object is not in.
The robot is asked for an object. Can you please bring coffee to the lab? And And basically, there is this problem of natural language processing of a command, which is the human asking, and the robot parsed bring as an action to go, so it's fine. It actually also knows where the lab is, I'll explain later, but is stuck with this object coffee, for which it does not know a location. So basically it says, I don't know.
My knowledge base. I will search the web using object eval to see if the object is in location, kitchen, office, meeting room, or printer room. Object.
There you go. So it goes to these, it calls this object eval, which is the thesis of my student Mehdi Samadi, finished the thesis, that is able to evaluate the truth of any statement on the web. So basically this robot asks, is coffee in kitchen? Is coffee in printer room? Is coffee in office? And this object eval, which is in its general form called open eval, returns a probability. And so object eval
Returns high probability for object copy in location office and also for object copy in location kitchen. Which location you think is best?
Now, again, the use of the human. The object eval returns something that says that it's equally probable that this object be in kitchen or in office. And it asks the human, what do you think where do you think I should go? And eventually this human says kitchen. And
I will collect the object.
and now the robot is done. It knows the object, it knows that it needs to collect it at a kitchen, and it knows that it needs to deliver it to the lab. So in some sense, the limitation, the cognitive limitation it had about the location of coffee is solved. So the robot asked to the web, asked the human, and it came up with the final
Copy
plan.
is delivered at the lab, room 7412. Is that correct?
Yes.
Okay, there we go.
I am now planning my route to specific room location. I am going to the kitchen, room 7600.
So there you go. And this robot is very kindly saying, I'm going, I'm leaving, bye-bye. But now, of course, it gets to the kitchen, and as you see, it has no way of putting coffee, taking coffee. It doesn't have arms. There's no way. What is a coffee machine? What is this thing about coffee? So what happens, how do you think that is going to handle this problem in this symbiotic autonomy issue? It will ask, and it just says happily,
Hello.
hello,
Could you please put the object
could you please put the object
coffee
coffee
and
in
press
my
done when
basket?
I am ready to go?
And press done when I'm ready to go. And there's a generous human, Mehdi Samadi,
Thank
who
you.
puts
Thank
the
you.
coffee
I am going
in
to
his
the lab,
basket
room
and
7412
eventually
delivered.
say thank you and bye-bye. Cobot does not parse any bye-bye, but people still talk with it one way or another, and there the robot goes to 7412, which is the lab. So this is an example of symbiotic autonomy in which indeed the robot found during its task several limitations. It did not know where's coffee, and then eventually did not know whether to go to the office or the kitchen, and eventually then offers, I think the lab is 7412, and performs its task. So basically this is an example of something absolutely specific to what I think robots, autonomous robots, should be about. They should be about doing things by themselves, but if not capable, they can resort to actually asking for help, be it from the web, be it from other robots, be it from humans, humans next to them, remote humans. So they should be in these kind of feeling what they can't do, what they can't understand, what they cannot see and perceive, just by using all these other resources that now in our digital world and in our environments are highly available. So this robot, though, very interestingly, learns from these interactions. So I just picked on two printouts of like files on, I put both the objects, but I was going to put the locations too. But you can actually show, you can see that the robot accumulates knowledge and can learn from this interaction with humans. And here is like coffees in 7602 with some weights, some value based on probabilities and frequencies and all sorts of like normalizations and all sorts of counting. And you can actually have the robot acquire knowledge by itself just by interacting with people. In fact, that's how he suggested 7412 as the location of the lab. Initially, people told Cobot, go to the lab, go to Manuela's office, go to the kitchen, go to Christina's office. And the robot also did not know where these locations were, and it asks people, where is the lab? And this 7412 is something very important, which is the robot knows where is the location 7412. So it kind of like connects what the robot knows, 7412, with whatever reference human use in language, Manuela's office, the lab, the kitchen, to the actual representation of the robot. So this is the example of symbiotic autonomy, using the humans to help the robot. Another use of the humans, which I find very compelling, is that we also developed methods for humans not to have to program the robots. They basically can instruct the robots using, as of now, some quite defined language. So it's not that I can just say, I like talk without a very kind of template-based language. But when we let these robots being instructed by humans, we invented this kind of like representation called instruction graphs that enable the robot to, a user to tell the robot some procedure, which doesn't matter what it is, it just matters that you can talk. And eventually, you can instruct the robot to do things. So these instruction graphs have robot primitives and apply to both our Baxter and our Cobot and also our Now. Any robot can have these robot primitives. And then basically these instruction graphs are actions, which are these nodes, and conditionals, which check some sensing primitives that the robot can have. They can loop while you don't see do something, and they can have references, which is do something that refers to a previous learned procedure. And they also can say something that says don't do anything, no ops. And here, for example, our Baxter at CMU has been only programmed with instruction graphs. Everything this Baxter does is, in fact, some motion primitives we had, lift up the arm, extend, go here, go there. Then we introduced all these skills, all these primitives, and basically all the procedures to do some more specific tasks, like the left arm, use its camera to see if the table is open, and the right arm pick up some object and put it there. All specific procedures were learned through these instruction graphs. Cobot also has learned the same structure, these instruction graphs, also to learn exactly where these different things, for example, here, there is a cafe on the 3rd floor of our building, and we would like to teach the robot to go and get coffee at the cafe. And it's not really a location that, well, it's in its map, but we didn't label it, so we taught the robot through these instruction graphs what was the path that it should take. So you should say, go forward that much until you see the counter. And we actually marked the counter with a QR code, but we could have a better detector, and then we say, approach this counter, ask for this, do this, come back. And it will go from the lab to this coffee place and bring back this coffee. So this becomes the actual go-to coffee, the go-to cafe plan. We have a lot of research on how to save all these plans, retrieve them, reuse them, adapt them. Actually, following up a lot on my own PhD thesis from 30 years ago or 25 years ago. A lot of like learning and correction. We also allow the human to teach the robot an instruction graph. The instruction graph gets executed, and the human may find that it's actually not that specific condition that I was looking for. It's not when you see the cafe. It's when you are like 3 meters away from that detection. And you kind of revise and can correct these graphs that are instructed. So this learning by instruction is also a very important manner to interact with humans. Humans can help, humans can, you can learn from humans, all these environment groundings, and you also can actually learn from specific instruction and correction. So this leads me to the final part of my talk, and then I'll be open for questions, which is about something that is very dear to my heart now, and that I would like to bring to your attention. Several of you are working in similar topics, and this is the topic of transparency. So the problem becomes very deep. We are all working on autonomous robots, or at least I am. Many of you probably are too. Others, but becomes this problem of autonomy. So I have to tell you something. When Cobot comes to my office is at the end of a corridor. Or when we see Cobot in the middle of the building, what happens is the following. Out of my office, I see Cobot going down the corridor. While I see Cobot, I can actually infer where it's going, because I'm seeing it. Then at the end of the corridor, the robot turns right or left, and for a little bit, I do not see the robot, but I can hear the robot. So I'm still fine. It's going. But then after some time, it's all gone. The vision, the hearing, and the robot is completely on its own. So at the beginning, when this happened, I used to call the lab where Joydeep was and Brian and say, did Cobot already arrive? Is Cobot already there? Or I would tend to follow this robot to keep seeing it. And then after some time, Joydeep kept telling me, don't worry, it will arrive. And I'm like saying, oh, are you sure? Because there is this thing about autonomy as something in which the machine, the robot, the AI system, is outside of our control. So this led me to be very puzzled about this concept. What happens when I don't see the robot, when the robot is by itself? This never happened when I have been doing research in robot soccer. And the reason is because in robot soccer, I always see the robots. I'm looking at the game, and I'm seeing everything. I might not know what's happening, but I'm seeing everything. With Cobot, it disappears. And the disappearing problem is really deep in terms of research. The opposite example is really the problem of actually, when Cobot arrives to my office, I would like to know what happened. Did you take Eric Horvitz down to the elevator? What happened? So all these problems about how to interpret autonomy are very difficult. So let me first focus on what is this problem of understanding autonomy in robot soccer, and then I'll explain about Cobot. So in robot soccer, many of you see videos of robot soccer. I also see videos of robot soccer. And the question becomes, how do we know what they are doing? And I tell you one additional thing. Most of the time when they do something wrong, and I ask my students, why did they do that? You know what's the answer? You know what they answer? What do you think they answer when I say, wow, why did they do that? What do you think? Anybody offers an answer? Say it again. Well, the answer is invariably, I don't know, right? So it's always like, I don't know. And that's like something extremely frustrating because how come you don't know? We are supposed to know what they are doing. But the environment is complex. So for example, here, if we would like to know, here is the ball, here is the robot, and if we would like to know what the robot is going to do, we would like to have the ability to actually show on the video the planning. It's going to pass here, and show that it's going to pass there. These arrows, there you go, were built after the fact manually. So my student Juan Pablo Mendoza took the video and annotated the video manually with this explanation of what was going to happen. That lets people look at these videos, understanding the autonomy of the robot very differently. Because now, on the video, you actually project all these things that eventually explain what is happening again. So, a PhD thesis of my student, Danny Tzu, is all about automatically annotating these videos. So we realized that the video, which captures the autonomy of that kind of like soccer robots, does not capture anything about why and how the robots are doing what they are doing. Of course, everything is known. The planner knows. It's all in the code. The problem becomes, how do we extract automatically from the code these reasons, these explanations of what's happening? So Danny is doing this thesis on automatically overlaying on a video, which is one of the best methods to capture what a robot does, all these explanations of what's happening. So here is, for example, on a drone that is doing some type of RRT planning, in which we project on the field the actual path and more markers, all chosen by the user. I want to see where the robot is, I want to see when it hits an obstacle, and eventually it does this. So what's beautiful about this research is that this is automatically generated, and for example, it has a very beautiful thing. All these red things here on the field are virtual. They didn't exist there on the field, so we can mix up reality with virtual virtual objects, and show, in this particular case, the planning that is going on. We do not show all the search as it's showing on the left on a GUI, but on top of the video, we project this. There is a lot of technical details that I invite you to read on his work about how to transform the coordinates of some static camera. Currently, Danny can do this only for static cameras. We are doing it also with 2 cameras, static. If the camera is moving, all the homographies between the actual positions of the robots and the video become much more complex to compute, but eventually he may be doing this thesis still moving cameras, but currently it's only for a static camera. So this enables you eventually to be able to do an explanation of what happened in this particular kind of initial video, in which the robot is there and plans to pass to one of these robots, and eventually selects a pass, which then plans to pass to another robot, and eventually, sorry, I touched this. And eventually, you'll see it does pass to that position. And then the planner evaluates again its moves and decides to pass to that position, and eventually kicks at the goal, knowing that there is an angle for which it has high probability of scoring. It misses the goal. Eventually, immediately the Kalman filter says the ball should go there. A robot positions itself, plans to pass to that point. Welcome to uncertainty, robotics. That robot computes it's going to shoot, misses the ball, eventually continues, again considers passing to the others or shooting directly, and has high probability it shoots. So look at this. This is something that is very deep, because one day we are going to have our world surrounded by autonomy, which is not just humans, but there are creatures that we really don't know what they are doing, and we have very difficulty in understanding what's happening. However, they are running code, and as such, this code can be such that they can reveal much more of their internals. So, going back to the cobot problem, so cobot again moves in our space, and cobot stops in front of an office, and there comes this kind of moment in which you wonder what happened when cobot was not close by. So questions in this autonomy become, what are you going to do next? What is your internal state? Which path did you take? What happened by the elevator? How long did it take to arrive here? Did you successfully escort Guru? Why are you late? So all these things are things that as of the moment, in order to answer them, we'll have to go in Python or C++, or we have to program the robot to answer all of this. It's all there. The robot actually logs his experience and everything is there. So what I'm trying to tell you is that I believe that for us in autonomous robots, one of the main challenges is going to be able to enable this transparency. So one work that we've done, which became the master thesis of my student Kim Baraka, was to explain what the robot is doing through expressive lights. So the robot actually generously has now LEDs, programmable LEDs, so that reveal the state. So if the robot wants to turn left, like in a car, the left side of its bottom LED starts showing. If it wants to turn right, it shows. So it announces to the humans what it's doing. So for example, one thing that was very interesting that we realized was that in this escort task, if you come to CMU, you are going to be mapped by this robot. You start following the robot, and you have no clue if my office is 3 kilometers away from where you are, 10 meters away. There is nothing. You are blindly following this robot. So there was this problem about letting people know, is cobot know, how far my office is? How much does it still need to travel? So Kim did this kind of like progress bar in these lights. And these lights start as blue, and as the robot moves, and the distance between where the robot is and my office decreases, this bar, this kind of column of light, becomes more and more green. We did some user studies, and of course we didn't have to be, it was no surprise to see that people would capture very well that as that column of light was being filled up, the distance was decreasing and they were approaching my office. Another thing is that when the robot stands in front of the elevator asking for help, press the elevator button, or at the kitchen, put coffee in my basket, or give me that object, or anything it's asking, it talks. If there is no human around, which may happen, the robot cannot keep talking. Talking is a kind of a very limited way to call the attention of someone. So now instead, Kim did these lights that show and start blinking in different colors. Not that the robot is very endangered, so the colors prove to be, through user studies, that blue is fine, but it blinks. And as it blinks, people approach the robot to find out what's the problem. And then the cobot says, can you please put that object in my basket? So these lights enable the robot to express more of its internal state. And when the robot is blocked by someone, it really throws at you these red lights, get out of the way, get out of the way, please excuse me, please excuse me. And people understand that unless they get out of the way, the robot doesn't move. So there is this issue about, this was one of the first attempts about having ways to express, in a way, the internal state of the robot to enable a better understanding of these autonomous creatures, which is the robot. And several of you have had IROS in the old days and nows currently. And we have to understand that the nows and the IROS from day one had LEDs, programmable LEDs, in their ears, in their face, also they have all sorts in the eyes, in the chest. These are remarkable methods to enable developers to really find what's happening with the robot. we used to use actually also the first IROS enabled us to program the tail. And we used to have the tail up or the tail down to know if the robot was seeing the ball or not seeing the ball. Very beautiful concept of trying to have something in the appearance of the robot to let us understand better what the robot's state is. Now the problem here is a bit more complicated because it's not about just the developer to understand its own code. It's actually about a regular human, a regular user, to understand better the state of the robot. Therefore, a lot of human studies in some sense enable us to find color that matters in terms of humans and also these types of different expressions that will be more meaningful for humans, like the progress bar and eventually like these blinking and all sorts of like different types of lights to enable the users, the humans, to trust more these autonomous robots. Then, the last thing I want to tell you is about something also very interesting in terms of actually explaining this problem of autonomous mobility of the robot. So let's think about what's a robot after all. A robot is some kind of like program that's running on that hardware, and we use ROS, we use whatever we use, and services and topics and everything, but it's really something that a regular human doesn't understand what's going on there. And the robots do things that humans understand very well, which is they navigate in corridors. You tell them, go to Manuela's office, and it goes. But there is a big gap between what it does and eventually what we understand how it does, or eventually how we understand how could it do differently. So the robot ends up having sensors, distance sensors, connects, laders, has maps that are labeled with, notated with positions X, Y, and poses, and all sorts of our robot thinking. So the first thing we try to do, and all these things in some sense are captured, we capture them in this autonomous life of the robot in a log. So we have, I forget, terabytes, more than terabytes. This robot keeps moving and accumulates at 60 hertz tons of data. So we have millions of bytes of these logs, and everything is there. As opposed to us, that our life is not all digital. The life of this robot is all digitalized. It's all there. I can go and check what happened on October 10, 2015 at CMU. I would know if Cobot went from here to there. Everything is there logged. So now the question becomes, how can we make use of that log to really have the robot explain to humans what's happening? So the first thing we did was that actually we did what many of us also do, which is to make use of the semantic annotations at maps. So somehow positions that are understood by the robot, 16072 minus 4333, which is some coordinates in the building where the 00 is somewhere, and these coordinates may be room. In fact, they are room 7004. So this left-hand side has no meaning for the robot, except to match with requests from humans. And this has only meaning for the robot and has no meaning for the humans. In fact, if you ask me what is this third kind of like component in this vector of positions, it's the pose. So the robot is supposed to know that F004 is some location in the building, which is that specific location, and when asked to go to this location, the robot should face the door in that particular setting itself according to its own 00 of its pose at that angle, 1.570. And these are, for example, these is, you can see that actually beautifully. These two offices are each one on one side of the corridor, basically on opposite sides of the corridor, and therefore the pose is opposite. So you either face this way or you face that way. But it doesn't matter. What matters is that there's all these semantic annotations. One thing that we did was take advantage of these semantic annotations, and then we have a sequence of actions. So the robot starts somewhere, navigates now in some corridors, takes some elevator, goes to another corridor, and these are pictures of the robot while it's moving by itself. So now the question becomes, how do we find out what happened? So we worked very hard and are still working very hard on what we call verbalization. As opposed to visualization, or similarly to visualization, our robots now are capable of verbalizing, converting its sound experience into language. And because this concept of talking about experience is not all of the same degree of detail, we introduced this concept of verbalization space to capture the different nature of explanations along 3 different dimensions: specificity, locality, and abstraction. And therefore, the robot can actually generate variable explanations for its sound experience. So it can say, I traveled 26 meters and took 152 seconds on the 7th floor, which is a very summarized explanation for what happened, probably here in this space. This is abstraction, specificity, and the number of words used. So very, very frugal in its words. It just says, that's it. Or it can say much more detail. I went straight for 15 meters and turned left, then straight for 51 meters and turned left, then straight for 10 meters to reach the destination. Or even more verbose. I started from room 3201, blah, 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 blah. So, very interestingly, now, if you come to CMU and when the cobot arrives to any place, you can ask, so where do you come from? Not yet, why are you late? That's the thesis of my student Vittorio Pereira coming. But you can ask the robot to explain the route it took. It still does not tell you why did you come that way instead of this way. It's all research to come. This is the beginning of an eternity of time to break the gap between how robots function and how humans function. And we need language. I do speak 5 languages, but unless I speak here in English, most probably I cannot reach out to everyone. So I have to bridge the gap between my brain and your brain so we can communicate. Same thing with the robot. We are going to spend a lot of time trying to get this robot language into human language, or human understandable methods of expression, be it lights, be it sounds, be it language, be it like all sorts of motion. We are in this business now, from what I understand, that my research is all about, on trying to have these robots explain themselves. Then it's beautiful to also try to learn to correctly infer an explanation level from language. So the robot may offer to a human a specific point in space, and the human might say, tell me exactly how you got here. And then we did some research on trying to understand that if it says no, now only tell me what happened near the room 7004, we did a lot of studies to classify this mapping between language and eventually how you move in this verbalization space. Can you only give me a brief summary? There you go. So the robot throws at you an explanation, and through dialogue, it is able to revise that explanation. So we did, you can see in the paper, we did several learning experiments with people and we showed results applying different methods that show that the accuracy of the robot generating the right explanation for the right language was it was able to learn to generate language for the right requests. So in summary, I'm left with my 10 minutes, sorry. In summary, I told you about the autonomous robots. We all know about tasks, localization, navigation, and maybe a few on autonomous data collection. Not many people talk about autonomous data collection. Is also one of my passions, is to get these robots to be useful in terms of gathering the vitals of our environments while they perform services. They can do much more while they move. And then I mentioned these three important aspects of these peer interaction with humans, namely symbiotic autonomy. They can help robots when the robots ask for help. This concept of learning from humans, the fact that humans can actually interact and tell you, go to the kitchen, get me coffee, and learning from going to the web, where humans entered all the information. And they can also learn by instruction. And finally, this fascinating topic that I invite anyone who wants to do a thesis on transparency to come and work in my lab on these automatic annotation of videos, expressive lights, and verbalization, which may lead to an increase of trust and accountability of humans on our autonomous robots. Thank you very much. And thank you.
Thank you for an extremely interesting talk. So you touched at the end on the people trusting the robot. Do you have any thoughts on whether the robot might trust the people too much? You push this button on the elevator and the person pushes the wrong button, puts the wrong object in the basket, and so on.
Yeah, I mean, people are what people are, so we know that they are not always trustable. But actually, our robots are very robust to, if in the example that you showed, if people would not press the right elevator button, the robot detects that it's in the wrong place when it gets out, comes back and says, I want to go to floor 8. Again, tries another human. And eventually, if all the humans at Carnegie Mellon would not be trustable, the robot would be in trouble. But it actually sends us email if it gets there stuck for more than 5 minutes, and it says, I've been here waiting to get to elevator 2, floor 8. Nobody helps me. Can some of my friends, Manuela and her students, come and help me? And we all leave whatever we are doing, we rush to the robot, press the elevator button, and done. So we can prove a theorem that says that there exists a set of people in the world who is trustable. And even if that set is only Manuela's group, I still prove the theorem.
Any other questions? Okay, go ahead.
So your cobots actually live in their robo world, right? And they are doing things in their robo world. Did they do in?
Sorry, I missed it. In their
Okay,
what?
so your cobots, they are actually in the digital robo world. They are moving around in a world which they design, right? They are observing the corridors, they are moving around and all that. Now, did they do anything in their world which was surprising to humans? So that you didn't expect the robo to do this in their world, and it did.
So that's a very good point. In fact, as I speak, every time I see cobot moving down in the corridors, sometimes I find that it goes too close to the wall. So I get kind of surprised that it's not a bit smarter about staying away from these walls. And in fact, yeah, it has its own representation. The challenge here is to break these difference between humans and robots and try to have humans communicate and correct and ask to robots at some level of understanding. This is a long way to go. I'm just saying that part of our research in AI, machine learning, and robotics includes now trying to have these robots explain themselves.
Okay. Last question, because me, I already alive. Okay. Last question over there.
So, is it?
So you mentioned at the end about collecting data. So I was wondering what you had envisioned for these robots. We see the robot initially going from A to B, but in its mind, it's actually thinking of many other things like collecting data, viewing people, maybe doing security. What are the types of things that you are thinking about in that area?
It's a very good question. So currently they only collect data that's about the vitals of the building. Temperature, humidity, noise level, all sorts of kind of like quality of air, Wi-Fi. It's only kind of the vitals of the building. But they could very well check if there is wet floor, if there is a faucet open, if coffee's in the pot, all sorts of other things. We don't have yet good sensors for those kind of like other metrics, but there is no limit to having a machine move around and collect all sorts of information. And the difference between a human moving around and the robot moving around is that when I move around, I tell you, I don't know my XY location well. I don't. Humans are not good at actually gathering their XY location. Robots, in our localization algorithms, are very good at knowing where they are. So combining the two things may enable people to assign better access points in a building, decide where they have to put air conditioning vents, all sorts of like features that currently humans do by intuition or by some kind of other design, but they never get data on whether their decisions were actually successful in achieving their goals. So we can, even these autonomous cars, imagine how much information we can gather about whether the leaves are already orange in the tree, or if the trees are like healthy, or if there is too much noise in that corner. The whole paradigm of mobility under a machine that can localize itself opens the door for these data, mobile data collectors.
Okay, Manera, thank you very much for wonderful presentation. Thank you very much. I close this kind of first plenary speaker since Metropolitan Government City Mayor Dijon arrived. Okay, so ready for opening ceremony. Thank you very much.